Welcome to the class 2 of Fermat's principle. So today we are going to study about the Fermat's principle. So let us begin with optical path. When light travels in a medium of refractive index, say mu, a distance say x with a velocity of say v, then the time taken by the light is t equal to x by v, or velocity is equal to distance by time. The path that a light ray follows as it passes through an optical medium or a system is oftenly called the optical path. The path that a light ray follows as it passes through an optical medium or a system is oftenly called as optical path. In the same time, the distance traveled by light in air or vacuum is called optical path. The distance traveled by light in air in the above interval of time is given by Ct, where c is the velocity of light in a vacuum, t is the time taken, where c is the velocity of light in vacuum or air. Therefore, the optical path Ct is nothing but, as you know, t is equal to x by v. Just substitute the value. C of t is equal to c by v into x. That is nothing but mu of x, where mu is the refractive index of the medium given by mu equal to c by v. Now the Fermat's principle. Fermat's principle of least time states that when a ray of light passes from one point to another through a number of media, it always takes the one for which the time taken is minimum. Remember here, Fermat's principle of least time states that when a ray of light passes from one point to another through a number of media, it always takes up the one for which the time taken is minimum, or the light follows the path of least time. Light travels between 2 points along the path that requires the least time as compared to the other nearby paths. So from Fermat's principle, one can derive the law of reflection, that the angle of incident is equal to the angle of reflection. The law of refraction that we generally known as Snell's law. The above statement of Fermat's principle, however, is not complete in itself, although it's true in some cases. There are situations in which it is found that the path followed by a ray of light is maximum, while in many other it is neither a maximum nor a minimum but a stationary. For an instant, in case of reflection and refraction in plane surfaces, the time taken is indeed minimum. But in the formation of images by a lens, where various rays from an object point travels over different paths to meet at the image point, the time taken by each of them is a stationary or a constant. Analytically, the law is therefore stated as, for a non-homogeneous anisotropic medium where the optical density varies from point to point. That is, the optical path, say L, of a ray, say AB, is given by L equal to A to B mu dl, is an extremum, that is either minimum, maximum, or stationary. Hence, in the refractive index of a medium, or mu equal to refractive index of a medium. Laws of reflection from Fermat's principle. The derivation of law of reflection using Fermat's principle is straightforward. The law of reflection can be derived using elementary calculus or trigonometry. The medium that light travels through doesn't change. In order to minimize the time for light travel between 2 points, we should minimize the path taken. So the first law, the incident ray, reflected ray, and the normal to the reflecting surface at the point of incidence all lie in the same plane. Now let us consider a plane mirror. This is the plane mirror. You can see. This is the plane mirror. Let us consider a plane mirror. A and B are 2 points above the mirror. So here we can take it as M1, M2, M3, and M4 is the mirror. This is the plane which is perpendicular to the mirror. Now point A and point B are the 2 points above the mirror plane and located in the plane, say A, B, C, and D, normal to the mirror plane. Light ray coming from A to be incident on a plane mirror and be reflected towards the B. Suppose the light ray passes through a point, say P, here. It means that the light is incident along A, P, and reflected along P, B. Thus, A, P, B is the most general conceivable path from A to B. Draw a plane ABCD normal to the mirror plane M1, M2, M3, and M4. Take the origin of coordinate at D. Let DC and DA be the x-axis and y-axis. Let us consider the distance DA equal to small a, CB equal to small b, and DC, this length, equal to small d. The point has general coordinates. The point has now general coordinates, say x, O, Z. If now AP plus PB, AP plus PB equal to L, then we get L equal to, by using a general coordinate systems, by using x, L equal to under root of x minus o, that is x minus 0 square, plus this length if I take, then I can say, by using a general coordinates, it is length is nothing but square root of x minus of this 0, because this is the distance along the x-axis, I can say, and y coordinate is 0 at the initial stage. Now this is the along the z direction, so it has the coordinates of x 0 z. At p, at a it is 0 a 0, at b is equal to small d small b and o 0, that is. Now that is L equal to x minus 0 square plus 0 minus a square plus of z minus 0 square plus square root of, if I take from this side, x minus d square plus of 0 minus b square plus of z minus 0 square. Or I can directly write the L as x minus 0 is x square, as 0 minus a square is a square, as z minus 0 equal to z square, plus of under root of, for the second coordinates, x minus d square plus of 0 minus b square, that is b square, plus of z minus 0 square is nothing but your z square. Now apply Fermat's principle to get the actual path. The path APB, that is this path APB, can be varied by varying x and z. We obtain the minimum value of length. That is the shortest optical path. To get the shortest optical path out of the actual optical path, we have to find the derivative of L with respect to z-axis and setting the derivative equal to 0. Thus, derivative of L with respect to z is nothing but the dou L by dou z by keeping x constant. If I solve this equation, that is L equal to under root of x square plus a square plus z square, that is the derivative of root x is nothing but 1 divided by 2 root x into x, 2x. Now here with respect to the z, we are finding the derivative of L. So 1 by 2 is nothing but 1 divided by, that is 1 divided by 2 root x into 2z plus 1 divided by 2 root x again for this content and 2z equal to 0. Therefore, simply we can write, or we can cancel 2 here and 2 here. We can write remaining terms z into 1 divided by under root of x square plus a square plus z square plus 1 divided by x minus d square plus b square plus z square equal to 0. So as a factor within the bracket cannot be 0. As a factor within the bracket cannot be 0 as it gives some constant value. We can consider just must be equal to 0, z equal to 0. The above results means that P must lie on the plane ABCD, which is normal to the mirror. If P coincides with that is O, here in this point, it is not a 0, it is O. It is obvious that the incident ray, that is AO, the surface normal on and the reflected ray OB lie in the same plane. And this is the first law of reflection. First law of reflection. That is, the incident ray, reflected ray, and the normal to the reflecting surface at the point of incident all lie in the same plane. Now let us go for the second law. The angle of incident is equal to the angle of reflection. Now let us suppose that a ray of light strike the mirror at O before being reflected to the B. First obtain the expression for the path length L. This is the ray of light from A, strike the mirror at O and gets reflected back to point B. First obtain the expression for path length L. What is the path length now? That is the distance traveled by the light from A to O plus O to B. The length L traveled by the ray from A to B, that is through O. In terms of, if I say small x, small l and A and B. Now minimize L by alternating the position of the point, say O. Then substitute the angles I and R. Now this is angle I, this is angle R. Or I can say this is theta I, theta R. Or I can take in the reverse order. The light is coming from this and going through this. Now the medium that light travels through does not change. In order to minimize the time for the light travel between 2 points, we should minimize the path taken. The total length of the light is given by L equal to, say, D1 plus D2. D1 means this length, AO. D2 is nothing but our OB. Now I want to find out the values of these two. Now let us consider the distances. Here it is. So from this point to this point, if I say it is x, and the total distance from this to this, if I take it as L, then what about the remaining terms here now? This is nothing but L minus x. If I take the distance from here to here is, say, x, and the length from here to here it is, say, L, then the distance between this to this becomes L minus x. And this length is, say, B, this length, say, A. Now what is the D1 now here? What is the D1? That is x square plus A square by using a Pythagoras theorem. That is this length. This length is nothing but A square plus x square. What about D2 now here? This length? Nothing but under root of L minus x square plus B square. When you substitute both the values, we get L is equal to under root of x square plus A square plus under root of L minus x square plus of B square. In order to minimize the path traveled by the light, we take the first derivative of L. As usual, while solving the Fermat's principle, in order to minimize the path traveled by the light, we take the first derivative of L with respect to x now. then dl by dx, x by under root of x square plus x square. How it will come? Now, in the previous equation we have solved, that is L equal to under root of x square plus a square plus z square. This is nothing but differentiation of this one, that is dou L by dou z. If I say, now this one 1 divided by 2 root x into 2x, 1 divided by 2, 1 and 2z. Likewise, if I solve the same equation, that is L equal to under root of x square plus a square plus 1 under root of L minus x square plus b square. This is nothing but dou L dl by dx. If I solve for x, then 1 divided by 2 root of x square plus a square into 2x, 2 to get cancels, and the remaining term becomes dl by dx equal to x divided by under root of x square plus a square plus of minus of under root of L minus x divided by under root of L minus x square plus of b square equal to 0. So set both the sides equal to each other. That is x divided by under root of x square plus a square equal to L minus x divided by under root of L minus x square plus b square. Now we can now tell that the left side is nothing but sine of theta I equal to right side we can nothing but sine of theta r. That is opposite side to the adjacent side. Opposite side to the hypotenuse. Opposite side to the hypotenuse. For the second, this is, if you take the diagram here, opposite side by hypotenuse. Opposite side by hypotenuse. Opposite side to the hypotenuse. So this becomes sin theta I equal to sin theta r. Taking the inverse sine of both the sides, we see that the angle of incident is equal to the angle of refraction, that is theta I equal to theta r. Hence, we have proved the second law of reflection. Now, if we go for law of refraction from Fermat's principle, the ratio of sine of angle of incident to the sine of angle of refraction is a constant for a pair of media for a given wavelength of light. Now let us consider x and y be a plane surface which is operating two media of refractive indices, say mu1 and mu2. Let a ray of light, say A, strike the surface of separation between the two media x and y at O and be refracted along OB. Let I and R with the angle of incident and the angle of refraction respectively. Let A and B, small a and small b, are the length of perpendiculars drawn from point A to the refractive surface, say xy, and from B to the surface xy. Let, now if I take m dash equal to D, MO equal to X, OM dash now becomes, as the length M dash is nothing but D, As the length MO is nothing but our x, then the remaining length OM dash becomes d minus of x. That is d minus of x. Now the time of interval from A to B, we can say it as t is, as we have already solved in the first case, t equal to L by, that is velocity equal to distance by time. Velocity equal to distance by time, or time equal to distance, here it is, by velocity. That is AO by taking V1 plus OB equal to V2. So AO is nothing but our x, OB is nothing but our d minus x, where V1 and V2 are the velocities of the light in the medium 1 and 2 respectively. To mark the speed of light in a different media, refractive indices named mu1 and mu2 are used. So, we know that V of 1 equal to C by mu1 and V of 2 is nothing but C by mu2. This we have already solved in the previous classes. From figure we can say here, you are seeing this. So AO, if you know the value of this length, that is A, once you know the value of this length, if it is x, then this is hypotenuse. So I can say this is nothing but, by applying Pythagoras theorem, under root of a square plus x square. In the same way, I can solve for OB. Here we know the value of this is b, and this length is nothing but our d minus x. So what about this length? This is nothing but b square plus of d minus x square. That is square root of b square plus d minus x square. Now substitute this equation in the previous equation. Substitute here, that is what we have solved it here. The length t equal to AO by V1 plus OB by V2. Substitute here. Now I am going to get the values like this. According to the Fermat's principle, t should be extremum, that is time taken to travel, is minimum. To minimize the transit time, we have to take the derivative with respect to the variable and set it to the 0. Therefore, dt by dx, that is the differentiation of time with respect to the x, if it equal to 0, as this is nothing but a constant value. So dt by dx equal to, this is nothing but this part. So differentiation of root x becomes 1 divided by 2 root x into 2x, where 2 get cancels. So remaining terms are x divided by under root of a square plus x square. If I substitute that value, now it becomes x divided by v1 under root of a square plus x square plus, this is nothing but minus of d minus x divided by v1 under root of b square plus d minus x whole square. Now equate these two. You take this one on the right side. Now this becomes, now as you know, x by a square plus x square So here, if I say, if this is sine I, this is sine I. Sine I is nothing but opposite side to the hypotenuse. What is this hypotenuse? Under root of a square plus x square. What is the opposite side? This is x. If I substitute that value here, now this part becomes this part, x divided by under root of a square plus x square becomes sine of I. Same way, d minus x divided by under root of b square plus d minus x whole square becomes sine of r. Now substitute this value. So I am going to get sine of I divided by v1 equal to sine of r divided by v2. Now take this one this side. So sine of I by sine of r equal to v1 by v2. That is nothing but our mu2 by mu1, or I can say it is mu1 sin I plus mu2 sin r is nothing but mu of 1 to 2, or sine of I divided by sine of r equal to mu of 1 to 2. So this is nothing but our Snell's law. Let us go for refraction at spherical surfaces. A transparent material, normally glass, bound by two surfaces, of which one or both surfaces are spherical, is known as spherical surfaces. You remember this? Refraction at spherical surface. A transparent material, normally glass, because we are dealing with a refraction, that means light is traveling from one medium to the another medium, bound by two surfaces, of which one or both the surfaces are spherical. Spherical. If the refraction, that is the refracting surface, is spherical, then I can call it as spherical surfaces. Lenses and mirrors have spherical surfaces. Hence, study of refraction at spherical surface plays an important role. So, basic terms associated with spherical surfaces are as follows. Now, here you can see a surface. This is spherical. Spherical. When the incident ray is incident on the surface, now here, if it gets through the medium, then I can call it as a refracting surface. Now here, we have to refer some points here, that's aperture. The aperture of a spherical surface is the circular face present to incident light. You remember this? The aperture of spherical surface is the circular face presented to incident light. That is the surface which is available here or presented to incident light. Or an aperture is the actual diameter of the circular outline of a spherical lens. An imaginary straight line passing through both the centers of curvature of lens is known as principal axis. Second one, we can go for a pole. The midpoint of the aperture is called the pole of the spherical surface. Midpoint of the aperture is called the pole of the spherical surface. Next one you have to remember center of curvature. The center of the sphere of which the spherical surface form a part is termed as the center of curvature. Center. The center of sphere of which the spherical surface form a part is called a center of curvature. Here you can see this C. A lens, either a concave or a convex, has two spherical surfaces, and each of these surfaces forms a part of the sphere. The centers of these spheres are known as centers of curvature. Now the principal axis, the line joining the center of curvature and the pole of spherical surface is called principal axis. Now, let us consider the refraction at spherical surface. Now consider this diagram. You consider this. Now this is the surface available for refraction. This is the surface which is available for refraction. Now the spherical refracting surface are two kinds, which convex or concave refracting surface. Let us now see the refraction of light at the spherical surface. Now, the change in the direction or bending of a light wave passing from one transparent medium to another caused by a change in wave's speed is refraction. You remember this. The change in the direction or bending of light wave passing from one medium to another caused by change in wave's speed. Why there is a change in wave's speed? Because the light is now traveling from one transparent medium to another transparent medium with two different refractive indexes. Here the refractive index changes, so the speed of light changes, and that is known as refraction. There is one medium with refractive index, say N1, and the second medium with a refractive index, say N2. Say here it is N1, I can take this one as N2. There is an object, say O. And a ray of light from O is incident on the spherical mirror. At N. Since it is moving from the rarer to the denser medium, it bends towards the line, this line. The ray bends towards this line. That is, otherwise we can call it as a normal drawn. An image is formed, and the radius of curvature of a spherical surface. Radius of curvature of a spherical surface. At this point, if it is say R with a center of C of a spherical surface. Let U be the object distance from the pole of spherical surface. That is from this point. This point, if I take U is the distance, and V is the image distance from the pole of a spherical surface which ray are incident, and N2 is the refractive index. If I take the same, So your line is little bit away from this. You consider this line from this one. Pole. So the distance between this point to the O is say U, and the distance from this point to the image, this is called the object distance, this is called the image distance, say V. Then we can say easily, we can say tan of alpha equal to Mn by Om. Tan of alpha equal to Mn by On. You can see this is the angle. This is the angle. So we can consider this one point here only, as there is a small change in the angle here, very small refracting surface with a small curvature. If I take it as a straight line now here, I can consider, now this is nothing but Mn by Om. This is nothing but alpha. Then the tan alpha is nothing but Mn by Om. In the same way, tan of beta becomes now Mn by M, here it is. M of I, tan of beta. Now the tan of gamma becomes now this angle. Beta is nothing but this side, tan of Mi, and this becomes Mc. Now I is equal to, now from both the triangles, angle I equal to angle NOM plus angle NCM, NOM and NCM. I is nothing but Mn by Om plus Mn by Mc, because this represents the angle R, this represents the angle alpha. So these two angles related to this. So as we have solved here, tan of alpha is equal to Mn by Om, alpha is equal to Mn by Om, tan of beta equal to Mn by Mi. There is a small correction here. Then tan of gamma is nothing but Mn by Mc. Now here I can say it is I is equal to Mn by Om plus Mn by Mc, and R is nothing but Mn by Mc minus Mn by Mi. Now from the Snell's law, we have N1 sin I equal to N2 sin R. So substituting the values of I and R from the equations 1 and 2, I get N1 by Om plus N2 by Mi equal to N2 by Mc. So this is nothing but, just substitute the values here. Om equal to minus U, Mi is nothing but plus V, Mc is nothing but plus of R. Now hence this equation becomes N1 by V minus N2 by U equal to N2 minus of N1 by R. Now here minus sign indicates just the direction. We are measuring it with respect to the opposite direction. Now the sign conventions here which you have to remember. Which you have to remember. All the distances is measured from the optical center of the lens. All the distances is measured from the optical center of the lens. All the figures are drawn with incident light traveling from left to right. You remember this? All figures are drawn with incident light traveling from left to right. If I take it as from here to here, if I measured it from O to M, I can say it is U. If I measured it from this to this, then I can call it as minus U. Only there is a change of sign in it. The distance measured in the direction parallel to the incident light is always taken positive, and the distances measured in the opposite direction of the incident light is taken as negative. You remember this. This is what we have taken here, minus. And the heights measured upward and perpendicular to the principal axis, distances are counted as positive, even though the height is positive, that is above the principal axis here. And the distance measured above and perpendicular to the principal axis is considered as positive, while those measured downward from principal axis are considered negative. Suppose if I measured the size of the object here above the principal axis, then I can take it as positive. If the image is coming here, and if I measure the image towards this side, the downward side from the principal axis, then I have to take it as negative. This is only the direction in which we are measuring the distance from the principal axis. The negative sign or positive sign gives only the direction in which we are going to measure the distance or length. The angles measured clockwise beginning at the optical axis are negative. Angles measured counterclockwise are positive. And focal length of a convex lens is positive and that of concave lens is negative. You remember this. You remember these sign conventions while you are solving for the equations of refraction at spherical surface or reflection or in some other equations in the optics.